Here are the you try it problems for chapter 10. Go ahead and remember to pause and try the problems as we go. So how would you carry out the following syntheses? Cyclohexene to cyclohexane, this would be butyl cyclohexane. Cyclohexanol to butyl cyclohexane. And cyclohexane to butyl cyclohexane. This is really a pretty challenging reaction, set of questions, because you've got to think in more than one step. You don't know any way to do this all in one step, but you've been learning that you can take cyclohexene to a halogen. Once I get it to a halogenated cyclohexane, I can use a Gilman reagent to couple butyl, the butyl group, to the cyclohexane. If I have cyclohexanol, you know you can take cyclohexanol to the butyl cyclohexane. And so that's just a slightly different reaction where I take the alcohol to the bromocyclohexane, and then I react it with the Gilman reagent to give butyl cyclohexane. And to take cyclohexane to the product, I have to somehow get a bromide on it. So what do? I do free radical bromination, and it gives me, which of the following is not a redox reaction? Well, if you look at 5, first of all, you can see that we added 2 heteroatoms to this double bond. 1 heteroatom on a carbon with 1 hydrogen would be considered the same oxidation level. So we basically have increased the oxidation level here. So that is oxidation. Here we've done the same thing. We've added 2 heteroatoms across the double bond. So now that is oxidation. Here we've added 2 hydrogens. So this is reduction. Here 2 heteroatoms, so oxidation. Number 1 is the only one in which you add both a hydrogen and a chlorine across the double bond. So this is not oxidation nor reduction. This is just an addition reaction. Okay, in the free radical chlorination of 2R-fluorobutane, you get 2-chloro-3-fluorobutane as a product. Which one of these is correct about the stereochemistry? Okay, to do this product, you first have to think about what is the reagent and what is the product. When 2-fluorobutane is chlorinated, you get 2-chloro-3-fluorobutane. So you've got a chlorine here. What is going to be the stereochemistry? Well, this carbon is unaffected by the reaction because the free radical would be right here, and the chlorine would pop on. But a free radical can invert back and forth. It can be, you don't have any preferential stereochemistry with the free radical reaction. So we're going to get both the R and the S chloro adduct. So when I compare the two products, I would see that the fluoro is always going to be R, but you can have R here or you can have S here. Those two compounds would be 2 diastereomers, and because there's really no preference in whether R or S is formed, they would be there in equal amounts. Which step in the mechanism of free radical chlorination will decide the regiochemistry of the product? Remember that regiochemistry is where the reaction occurs, is what that says. Regio stands for where or region of the molecule. So what is going to decide the regiochemistry of the free radical chlorination of 2-methylpropane? Well, if you think about the mechanism is that a chlorine free radical plucks a hydrogen off, causing a carbon free radical. That carbon free radical then is chlorinated, and the chlorine goes in there. So where the chlorine goes all depends on where the free radical was. The free radical is determined by which hydrogen is abstracted when the formation of the free radical happens. So the correct step is this. The dipole moments of methyl chloride, methyl bromide, methyl iodide, and methyl fluoride are given here. So this is for the fluoride, that's for the chloride, that's for the bromide, and that's for the iodide. What is the best explanation of why these don't change a lot? See, fluorine's really electronegative. You would expect that it would have the absolute hugest dipole moment, but they're all about the same. Why would that happen? Okay, if I look at this and I consider the electronegativity of the halogens, the electronegativity of the halogens is not constant. For fluorine, it's 4. For chlorine, it's 3. For bromine, it's all the way down to 2.5. And for iodine, it's down to 2.1. So there's a significant difference in the electronegativity of the halogens. So number 1 is not the reason. If we look at number 2, the inductive effects are counterbalanced by hyperconjugation. Hyperconjugation is on carbons that are substituted with other carbons. There's no substitution on this carbon, so it can't be that. The electronegativity effects are counterbalanced by bond strength. Well, the carbon-fluorine bond is going to be really, really, really strong, and the carbon-iodine bond is going to be a lot weaker. That's not really going to explain the electronegativity effects. A stronger bond doesn't affect the dipole moment. It doesn't have any effect. Okay, lone pair electrons are more delocalized on smaller halogens. It's actually the other way around. Lone pair electrons are more delocalized on a big atom than on a small atom. Then the charge separation and bond length trends have opposite effects. Well, charge separation is the measurement of the degree of difference in electronegativity. And so as I go from carbon fluorine down to carbon iodide, you would have a much smaller difference in charge separation of the del positive on the carbon to the del negative on the halogen. The bond length trend is that the longer the bond, the greater the dipole moment. So you actually see that as charge separation starts decreasing, the bond length is increasing, and so they do have opposite effects. This was a real hard problem, and unless you read the chapter in great detail, you would never have gotten this. Which of the following is not the product of a free radical reaction of 2-pentene with NBS? Well, if I look at 2-pentene reacting with NBS, N-bromosuccinimide is going to provide a low concentration of the bromine free radical, which increases its selectivity. That the increased selectivity is going to give you a free radical addition of bromine in the allylic positions. So I can get free radical bromination in the number 1 in the number 4 position. So this is free radical bromination in the number 1 position, and this is free radical bromination in the number 4 position. This is just flipped over right here. This one's shown just the way it comes. Now, that explains these two as being products. I look at the other two, and what do I notice? First thing, notice, this bromine is not allylic to this, so this would have a hard time forming. This is allylic to this double bond, but the double bond is in the 1 position, not in the 2 position. How could that happen? Well, this 2-pentene, when it forms a free radical, is stabilized by resonance. So the resonance puts the free radical here on the number 1 carbon with the double bond on the number 2 carbon, or when it flips over in its resonance, you would have double bond on the 1 carbon with the free radical on the number 3 carbon. And that explains the formation of this bromide. So the product that is not formed from 2-pentene and NBS would be this compound. Which of the following radicals would be the least selective? Okay, when I look at this, I look at selectivity. What do we know about selectivity? Selectivity occurs when you have something that is somewhat stable and can take its time to react and select for the most stable product. When you have something that's highly reactive, it's so reactive, it just reacts with anything in any way that it possibly can, and that reduces the selectivity of that species. So if I look at these free radicals and I look at the stability of them, that's going to tell me which one will be the most selective. If I look at the halogens, I know that stability of the free radicals goes from iodine down to bromine, down to chlorine, and fluorine is the least stable. So, least stable, so this would be the least selective. Now I compare it to the hydroxyl free radical and the fluorine free radical. Which one of these would be the most selective? Well, the hydroxyl oxygen free radical is a bigger atom, and so it can stabilize that free electron a little bit better than the little bitty tiny fluorine free radical. So the least selective free radical here would be fluorine. What is the best way to accomplish this transformation? The best way to accomplish this transformation would be one of these reagents here. So if I look, phosphorus tribromide, what do we use that for? We use that for changing an alcohol to a bromide, so this will not do it. Hydrobromic acid, we use that for adding bromine across a double bond, and that would not give us bromine in the allylic position. All of these compounds are going to generate free radical bromination. However, this bottom one doesn't have anything to help the NBS decompose, and the water is going to interfere in that reaction. So this is not a good way. Now, NBS and bromine both will give you allylic bromination, but NBS, because it gives such a low concentration of bromine, will give you the greatest selectivity, which would give you the most of the bromine in the allylic position. So this is the correct answer. What is the best way to convert this alcohol to this bromide? Okay, if I look at all these reagents, these are all for doing bromination. And if I look at this, I see I can either use hydrobromic acid or I can use phosphorus tribromide. Hydrogen bromide is what we use for a tertiary alcohol. Phosphorus tribromide is used for a secondary or a primary alcohol. I look at my alcohol and I see it's tertiary, so then I know this is the correct answer. So how are you going to convert bromine to a deuterium. Remember, a deuterium is just hydrogen, but it's with an extra neutron in the nucleus. Okay, if I look at this, if I use KOH, that would remove hydrobromic acid from this and give me the alkene. And then if I used hydroboration, deuterated boron in THF, I would get a boron and a deuterium being added, but I would get the deuterium being added in either of two places. There would be no selectivity. And then you'd have to reduce the boron off and it would give you an alcohol. So something's wrong there. If I look at KOH, which again would give me the alkene up here, followed by sodium borohydride, sodium borohydride is a reducing agent that does not reduce alkenes. And not only that, you don't see any deuterium anywhere in there. Okay, let's look at the bottom one. Sodium hydride is an excellent base. That would remove hydrogen bromide to give you an alkene here, followed by deuterium and palladium. That would put two deuteriums in, not just one. If I take lithium in pentane followed by hydrogen copper iodide, well, you would get the lithium replacing the bromide, but hydrogen gas is not going to react with lithium bromide. Magnesium in ether forms a Grignard reagent, followed by a product, deuterium oxide, which is a protic compound. Remember, Grignard reagents react with protic compounds to put a hydrogen, or here a deuterium, in place of the magnesium. So this is the correct answer. Which of the following molecules would not yield the desired organolithium reagent when treated with lithium and pentane? As long as you have an organohalide that does not have a protic group in it, when you treat it with lithium, what are you going to get? You're going to get the alkyl lithium compound. All of these compounds have a halogen there and no protic compound, no protic functional group, except for number 2. If I treat this with lithium, not only will the lithium halide the lithium alkyl lithium compound that forms react with the protic part from the alcohol, but the lithium will react with the alcohol itself and form an alkoxide. So this compound will not give an organolithium reagent. That protic thing won't work with organometallic compounds. Okay, what is the IUPAC name of this molecule? If I go to name this, the first thing I do is I find the longest chain with the chlorine on it. That's going to be 6. So it's going to be a hexane. Oh, excuse me, 7. 1, 2, 3, 4, 5, 6, 7. There's 7 carbons in the longest chain. So then I'm going to number the substituents. What are you going to get? You're going to get 2 chloro, then 4 and 6 methyl. So it's 2 chloro, 4, 6 dimethylpentane right there. What is the product of the following sequence of reactions? Well, reaction of an alkyl halide with 2 lithium gives you the lithium will replace this iodine right here. Then if I mix that with copper iodide, we get the Gilman reagent because the 2 alkyl groups will then be attached to the copper and it'll be a copper lithium compound. Then if we take the Gilman reagent and put it in contact with an alkyl halide, you get a coupling reaction. So this carbon is going to end up being attached to this carbon. So let's see if we can find that compound somewhere there. So you would have 1, 2, 3, 4 would be the double bond. and then 5, 6, 7, 8, 9 with a methyl group. So let's go ahead and look and see if we can find it. If I look at 1, 2, 3, 4, 5 is correct. That one works. This one, you see you have the alkene on the number 4 carbon. This one will not work because the alkene is not on the number 4 carbon. This, the alkene's on a number 4 carbon. This, the alkene's on a number 4, and this one. So now what we have to do is look to see about the rest of the molecule. If I look at the rest of the molecule, what would be attached to the carbon on the 5 carbon in the double bond would be basically an isopentyl group. You can see the Pac-Man mouth. I don't see a Pac-Man mouth here. I don't see a Pac-Man mouth here, but there's one here and there's one here. Let's take a look at the two compounds to see which is which. If I look at this one, you can see there's 3 carbons, 1, 2, 3, 4, and then you've got 2 carbons attached. Here you've got 1, 2, 3, and then 2 carbons attached. Let's see what we've got over here. We would have 1, 2, 3, and then 2 carbons attached. Altogether, the compound should have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. Let's look at this product and check to make sure that's the right number of carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is the correct product. How many constitutional monochloride isomers will form in the free radical chlorination of 2,3-dimethylpentane? So basically, this question is saying how many isomers can you get of one chlorine adding to this in a free radical reaction? To do this, we've done these kind of problems before. What you do is you count the number of different carbons. 1, 2, 3, 4, 5, 6 different carbons will give you 6 different products. This reaction produces 5 products. Why does it produce so many? Because you've got 1, 2, 3 allylic carbons, and then what you also have is resonance occurring, so you get kind of a mess. But one of these is not, one of these is the product, the rest of them are not. Which is the possible product? Well, the first thing I do is I look for allylic compounds. This is not allylic. You see, up here would be allylic. This is not allylic. Here, here, or here is allylic. This is not allylic because there's not even a double bond. And this is not allylic because it's 1 carbon away from the allylic position. The only product that is allylic is this one, and that would be the one you select.